So let's start today with sketching a rational trig function. So in our list of um, steps that will be important for graphing, let's start with domain. Can someone tell me the domain of this and how to find it? Let's just start with how to find the domain. Okay, we can go step by step. Is there anything wrong with sign when you plug in stuff for x? It's the domain of sign. Yeah, domain is everything. How about cosine? That's the same thing, right? So think about when you plug values in for x, what are the only problems that might happen? Look at the function as a whole. What problems might occur if you plug values in for x? Yeah, values might cancel. Um, so with values cancel, it's just going to be 1, right? But so when talking about domain, I'm saying, are there any x values where you have a does not exist value? Does that make sense? Like, if you plug something in for x, could you get something that doesn't exist? Yeah, like a vertical asymptote. That would be an example. Like, how would you find that out? Okay, so let's talk about domain again. When not when so when x equals 0, you get 0, which is fine. Think about another angle. So where do you look at for the domain? So domain means what values are valid for x. So usually the question for domain is what values aren't valid. So what I mean by that aren't valid, what sorts of things can have domain problems? Okay, let's pretend it's x over x plus 1. What's the domain here? Yeah, x can't equal 1. Why not? Okay, wide undefined. Right, you have something divided by 0. So what's any different than this problem? So when I ask for domain of this, why can't you use the same, you can use the same logic here, right? You answered this one quickly, right? Because that sets the denominator equal to 0. So it's the same deal here. What values of x make the denominator 0? It's no different of a question. Yeah, x cannot equal pi. So x cannot equal pi. Can it not equal anything else? Yeah, 3 pi would be an example. Anything else? 5 pi, yeah. What's a pattern here? Yeah. X cannot equal pi plus 2 pi n, or if you want to rewrite that, x cannot equal 2n plus 1 pi. So this is odd multiples of pi. So again, why is that? Pi is where cosine is -1, and this is on negative infinity to infinity, right? So I have to include everything. Okay, so that's when it may not exist. Does that mean they're vertical asymptotes? So here's the domain. All x such that x is not equal to 2n plus 1 pi. Is x equals 2n plus 1 pi a vertical asymptote? Why not? So the range of sine is -1 to 1, and the range of cosine is -1 to 1. But notice when you divide by something close to 0, that means it shoots up, right? So we don't know what the range of the whole thing is because we're dividing. Does that make sense? Sine and cosine's range is -1 to 1 respectively, correct? But, for example, how about sine divided by tangent? Or sine divided by cosine, which is tangent. That doesn't have range -1 to 1. Okay, so the domain does all odd multiples of pi are not in the domain. So is odd multiples of pi a vertical asymptote? Or what else could it be? If not a vertical asymptote, what else would it be? A whole, yeah. How do you know which? How do you think? How do you mathematically describe the difference between a vertical asymptote and a whole? Something to do with stuff we did in the beginning of the semester. Good, limit. So let's do the limit. Actually, before that, yeah, so we would need to do the limit as x approaches. Let's just do pi. And then we'll see why everything else follows from pi. How do you calculate this limit? We haven't gone through all the sections yet, so the next section, after this section is optimization, and the one after that, I think might be anti-differentiation. Good, yeah, multiply up top and bottom by 1 minus cosine, good. Yeah, so maybe like a couple classes after the last class that we do. That's the quiz. Okay, good. That was a good step. Multiply the top and bottom by 1 minus cosine, because when you do that, you get a product of a difference of 2, or you get a difference of 2 squares in the denominator. Okay, now what? Also good final practice to do limits for the final. So why is getting a 1 minus cosine squared good? What can you do with a 1 minus cosine squared? Yeah, it's a trig identity. Do you remember which one it is? Right, it's sine squared. So we have limit as x approaches pi of sine of x, 1 minus cosine of x, over sine squared of x. Okay, so we have a sine and a sine cancel. So what's the limit? What happens when you plug in pi? What's cosine of pi? -1. What's sine of pi? 0. So if you have a limit that's, so this is like infinity, right? Plus or minus infinity. So if you have an infinite limit, what does that tell you? Is it an asymptote or a whole? Asymptote, correct. Okay, so just by the way, if you can see why we're doing all these steps, when you plug in pi into the beginning, you get 0 over 0. Right, so that's we don't know what that is. It turns out in this case, it happens to be infinity. Okay, so how do we know what happens at the asymptote? Right? Maybe it can go up like that, it can go down like that, but maybe it goes down like that and then up like it here, or maybe it goes up here and then down here. How can we figure out which direction it goes? Good, check left and right limits. Okay, so we can use this final form. Actually, we can use whichever form we like. Well, actually, let's use the first form. Let's just use this one here. Sorry, let's use the final form. So let's start with the left. Okay, so as x approaches pi, is 1 minus cosine positive or negative? So cosine is negative, but 1 minus negative is positive, yeah. So it's 1 minus negative, so which is positive. So the numerator is positive. Okay, and the denominator, as x approaches pi from the left, what does it mean from the left? in a unit circle, what quadrant am I in if I'm to the left of pi? So left means less than. Oh, is that positive for sine or the other one? Oh, okay, yeah, so 1, that's true, but when we do limits, we only care about close values to the left, so just 2. So it's positive. So that means when you approach pi from the left, you get infinity. Let's do the same thing to the right. Okay, so similarly, what's cosine to the right of pi? Close to the right of pi? Is it positive or negative cosine? Negative, correct. And then is sine positive or negative? Negative. So that is, so 1 minus negative is a positive, because minus and negative is always plus. So negative infinity to the right of pi. Okay, so that's the solution. So the domain, so we have vertical asymptotes. At odd multiples of pi. And to the left, it goes to infinity, to positive infinity, and from the right, it goes to negative infinity. Okay, can someone tell me why it's good enough just to do pi and not, do I have to do 3 pi and 5 pi and 7 pi? Why is it good enough just to do pi? The pattern repeats correctly. Correct. When does it repeat? After how many does it repeat? Yeah, but at 3 pi, how do you know it's positive, negative infinity? How do you know it's even a vertical asymptote? Like, do I need to do a general formula for n? Or can I use something else about sine and cosine that allows us not to need to do that? So you see the question? We only did the proof for pi, right? But there's a lot of asymptotes or domain errors. So what do you know about sine and cosine? Yeah, so you have the right idea. The pattern repeats, but not just because you see it in the domain, but it's because sine and cosine are periodic. You see, for example, if you had x over 1 plus cosine, yes, you still have the same domain errors, but this is not periodic. So you'd have to maybe do something a little tricky when trying to figure out asymptotes here. You might have to actually do something with 2n plus 1 pi. However, sine and cosine are 2 pi periodic. So what does that mean? So sine of x plus 2 pi over 1 plus cosine of x plus 2 pi is equal to sine of x over 1 plus cosine of x. That's what it means to be periodic. So what does that mean? So graphing on 0 to 2 pi, is enough. So that's why we only really need the pi example. Any questions on that? Whenever you have a trig function, you should check for periodicity. So maybe we can even put that as an extra step here. Maybe 3a. Check for periodicity. Periodicity. Okay, all that's to say that it's good enough just to do pi, and then we're done. Okay, so this is periodicity. Okay, so that was all for domain, which led into absolute and led into vertical asymptotes. So let's do the other parts of our list. X and y intercepts. That was the other part. So this was, remember, sine over 1 plus cosine. Okay, let's start with the x-intercept. How do you find the x? Actually, no, y-intercept is always easier. How do you find the y-intercept? Right, set x equal to 0. So if you do that, you get sine of 0 over 1 plus cosine of 0, and that's 0. So the y-intercept is 0, 0. Okay, how about x-intercept? Set y equal to 0. Okay, what's the answer? How do you solve this? Yeah, so how do you solve for x? So I agree with the sine equals 0, but you don't want 1 plus cosine x equals to 0. Because then you get 0 over 0, or you get 1 over 0. You see why? You want to set both of them equal to 0. Oh, I see. If you set 1 over cosine x equal to 0, well, nothing is true, right? It's never equal to 0. You're thinking of it as a product? Yeah. That'll never equal 0, right? So just sine equals 0. When is sine equal to 0? Yeah, both of those. One of those is more right than the other. So this is true in general for sine, right? However, can someone tell me why this answer is better? For x-intercepts? This is true when sine is equal to 0, but why is this true for x-intercepts? So we mean by inverse. I mean, you don't have to be so... Oh, okay. Well, yeah, it is the domain. Yeah, do you see why it's the domain? Because this is when sine is equal to 0, but you don't want the place where 1 plus cosine is equal to 0, because we already went through that. That's when you have a 0 over 0. Since the 2n plus 1 pi are not in domain. Do you see that? It's because of the denominator. That's why you have to exclude. Yeah, so whenever you're solving for 0 and you set numerator equal to 0, you always have to make sure that the denominator is not also equal to 0 there. So that's what's going on here. Maybe I'll spell that out. Whenever you set numerator equal to 0, numerator, numerator, you should check if denominator equals 0 there. Everyone see why that's true? All right. All right, so for our example, we have x equals 2 pi n. So for x equals 0 and 2 pi, these are x-intercepts in our repeated domain 0 to 2 pi. So when we're just going to graph 0 to 2 pi, we only really care about these 2 points. And then we say the rest just repeats itself. Okay. So any other questions about this? So when dealing with x-intercepts, when you have like fractions, whenever you solve for 0, just make sure the denominator is not also equal to 0, because then it's not an x-intercept. Because in this example, it's actually infinity there, which is yeah, 2 pi n is cosine's never equal to 1, right? We don't want we don't want cosine to equal -1. That's the point. Cosine of pi is equal to -1, so that we need to exclude that. Right? This includes all odd integers, odd multiples of pi. That's where cosine is equal to -1. Do you see that? Cosine pi is -1. This is cosine pi. So right, these are even and these are odd powers, multiples. Yeah, that's right. Cosine 3 pi over 2 is 0, and cosine of pi over 2 is 0. But yeah, we just care about where sine is equal to 0. And some of those points, cosine's -1, so we want to exclude that. So like, for example, when you plug in pi, you get 0 over 0. But we know what happens at pi. It's an asymptote. Okay. So what was after the x-intercepts? Oh yeah, it was the vertical asymptote like we just did. Okay, how about horizontal asymptote? Can someone tell me why or why not there exists a horizontal asymptote? It has to do with something we established earlier. We could just do it. Let's do it. Let's do the limit. And then we'll see why we can do something different. How do you solve this limit? Well, final review. Do you remember how to solve these types of limits? That would be limit to 0, right? Which we don't have here. Right, this is limit to infinity. Here's a simple reason. It's periodic. If this thing repeats itself forever, right, does that mean it ever approaches anything? Like, let's say when we graph it, it looks like this. Well, it won't look like this because there's an asymptote somewhere, right? Let's say it's like that. As x goes to infinity, and all I'm doing is copy and pasting this thing off for infinity, is there a horizontal asymptote? You can't, right? Non-constant periodic functions never have a horizontal asymptote. Do you see why? A horizontal asymptote is defined by the limit, right? Limit as x approaches infinity of f of x, that equals horizontal asymptote. But if f of x is periodic and not constant, then you always have different values. Then you always have different values, i.e. f of x does not approach anything. It always repeats itself. Does that make sense? So just for like the same reason why sine doesn't have a horizontal asymptote. So in general, periodic functions never have a horizontal asymptote, except for the obvious constant, right? Okay, so that's good for horizontal asymptote. There is none. Okay, symmetry. Let's see if there's any symmetry here. Okay, what's symmetry again? What do you plug in for symmetry? Negative x. Yes, let's do that. All right, now what? Here's a hint. Okay, here's an angle. Can someone tell me where the what quadrant the negative of that angle is in? Or how do you even define a negative angle? Not quadrant 3. That'd be like plus. Yeah, it'd be quadrant 4. So this would be you're not that kind of negate, but negate means so sweeping up here is the angle. So sweeping the opposite direction is the negative of the angle. What's the relationship between this point xy and this point? When you you're in the negative angle? If this is xy, what's this point down here? X negative y. Good. Okay, so what's sine of negative x? Good. It's odd. Sine is an odd function because when you do the negative of the angle, what happens to sine? It gets negated. Okay, what's cosine of negative x? Cosine. And why is that? Because when you negate the angle, the x doesn't change. So, is there symmetry? Look closer. Now is there symmetry? It's not even symmetry, if that's what we meant, but it might be the other one, right? It's odd symmetric. Okay, so the facts here, where sine is odd. Everyone see that? Everyone okay with that? So when we take out the negative, what's inside is f of x. So we have f of a negative x is equal to negative of f of x. So our thing is symmetric. Okay, so what's next on our list? Periodicity. Okay, now we can go. Okay, we did asymptotes. Okay, let's do increasing, decreasing. Okay, now we can do calculus. Okay, the limits were part of calculus. Okay, how do you determine if something is increasing or decreasing? Yeah, find critical numbers. Question: does it make sense why it's good enough just to find critical numbers on 0 to 2 pi? This is periodic. So whatever happening in 0 to 2 pi, it's happening everywhere. So just 0 to 2 pi is enough. Okay, so how do you find critical numbers? Yes, first the derivative. Okay, so this is quotient rule, so the derivative of sine is cosine times 1 plus cosine minus, then the derivative of 1 plus cosine is negative sine, and times sine. It's all divided by 1 plus cosine squared. Okay, so we get cosine squared of x plus cosine plus sine squared of x. Okay, can we do anything? Can we simplify? How can you simplify this? You can, by the way. Actually simplifies very nicely. You don't need to factor out cosine. Yes, we have a trig identity. We have cosine squared plus sine squared, that just equals 1. And now what can you do? Now you can cancel out that 1 plus cosine. Okay, so the first derivative is very nice. All it is 1 over 1 plus cosine. So what are the critical numbers? We actually have found these already. What are critical numbers again? Not 2m pi, it's the other one. So that's one of the cases where the derivative is equal to 0, but do you see this is never equal to 0? So the other, yes, that was the other characteristic of a critical number was when the function, meaning the derivative, is undefined, which is 2m plus 1 pi. So when we do our first derivative test, we only need to test around pi. We kind of already know this by our asymptotes, but let's just do it. So we know that there might be a change in the derivative around pi. Okay, so what's the value of the derivative before pi? So when you plug in something before pi, what is this value? Well, let's ask this. Look at 1 over 1 plus cosine. Is that thing ever negative? Yeah, this is always positive. So just notice you didn't even need to do this testing. 1 plus cosine is always positive because 1 plus cosine is always positive. Everyone see that? You know, of course, except for 2n plus 1 pi. Let's say in its domain. Everyone see that? Because the range Okay, so any questions on this? So this is an always increasing function. There's this asymptote at pi. So I think we determined what was happening at the asymptotes. To the left, it's going to infinity, and at the right, it's negative infinity, which makes sense. Right? Going to the left, it's going to positive infinity, which is increasing, and to the right, it's negative infinity, which is increasing. Okay, any questions on this? All right. Is there a max, local max or min? Yeah, no. Yeah, you can see that, right? There's... Oh, be careful. Okay, let me ask you this. If this were negative here, would that give you a maximum? Why or why not? It's just an imaginary scenario right now. If that was negative instead of positive, the derivative to the right of pi is positive or negative. Would that give you a maximum? Think about the function. You have a change in derivative from positive to negative. Are you sure that implies a maximum? What also needs to be true at the sign change? What is the maximum? What would the maximum be? So you say yes. Say what the maximum would be, and then you'll see why. Yeah, left and right. So what's the maximum? Once you say it, then you'll see why it's not the maximum. In this case, it's not continuous. Right? That was the other thing you needed, right? What's happening at pi? It's an asymptote. So what is the maximum? The maximum is f of pi, right? That's the definition of the maximum. Oh, you don't even need continuous. It's just the function needs to exist there, right? No, sorry, no, you do need continuous. You could have something like that. Yeah, that would be a negative derivative, positive derivative, and not a maximum. Yeah, so you need to be continuous, and it needs to exist there. So do you see that? If you have an asymptote, it'll never be a max or a min. So just want to make sure. the maximum is a specific point. And it needs to be continuous because you can have weird examples like that. Okay. All right, what was next on the agenda? It was second derivative, right? Concavity. Okay, so our first derivative, we simplified down nicely to 1 plus cosine. Okay, now let's do the second derivative. Okay, is there a way to do this without the quotient rule? Can you do the derivative of 1 divided by 1 plus cosine without using the quotient rule? Good, yeah, I always do this whenever there are reciprocal functions. I just treat it like a chain rule. So notice how quickly I'm going to do this rather than doing the whole quotient. So this is negative 1 plus cosine to the negative 2 times negative sine. So it's sine over 1 plus cosine squared. I think that's a lot easier than going through the quotient. Okay, so what's the deal with concavity? How do you deal with concavity? How do you determine where something is concave up, concave down, etc.? So hint, you use a second derivative somehow. Yeah, so how do you determine where it's positive or negative? Yeah, so find where, so remember, just because the second derivative equals 0 does not mean it's an inflection point, but it's where might an inflection point be. So we have to find where it's equal to 0 and where it doesn't exist, because that could always also change inflection. All right, so we know what these are, right? What are these values? Where do these things happen? Yeah, 2n pi is where it's 0. And more, right? And then you have to also include the does not exist places. And pi, yeah. So maybe do like a different symbol for the does not exist place. Yes, we still need to include pi because the sign may change. Okay, what's the concavity before pi? So first of all, look at 1 plus cosine squared. That's always positive. So this is nice. All we have to do is determine sine. What is sine between 0 and pi? Positive. That's concave up. What's the concavity, or what's sine between, yeah, negative. Okay, question. Why don't I care about concavity there and concavity there? Do you know what it is? You should know what the concavity is. What's concavity before 0? Yeah, it's periodic. So which one do you think it would be? Negative, yeah. It's going to share it from here. And then this one repeats over here. So based on that, okay, so yeah, let's think about inflection points later. Concave up. So it's concave up on all multiples of 0 to pi, right? So if you just copy and paste this, it would be 2 pi n to 2n plus 1 pi, and then concave down in the other places. So that's the odd multiples, starting at the odd multiples, and then ending at the even multiples. Okay, so again, for graphing purposes, just 0 to pi and pi to 2 pi is enough. Okay, what are the inflection points? Be careful here. No, I think there are inflection points. But you're right to be careful. Something is not an inflection point, though it looks like one. So, right, what is an inflection point where the concavity switches places, right? So this does switch, and 0 is an it exists, right? So, and same thing with 2 pi, right? So it's 2 pi n. Why is pi not an inflection point? Yeah. So, right, inflection points need to exist, right? It's a point on the graph where the concavity switches. So even though there's a change of sign around pi, but pi is an asymptote. Similar to why there's no max at an asymptote. Like little thing here, right? We were exploring if there was a negative here, it would not be a max. So similarly, since there's an asymptote here, it can't be an inflection point. Okay, let's just, I kind of forgot what the original function was. I think it was, yeah, that. So let's just find f of 0 is fine, right? Because it just repeats itself. So it's 0. So at 0, 0, so 2 pi n comma 0 are inflection points. All right, that's a lot of information. So let's graph it. And then we can take a break. Okay, we said it's enough just to look at 0 to 2 pi, and then things repeat itself. Let's give ourselves some room. Okay, let's start from the beginning. Okay, we had an asymptote at pi. All right, I'm going to type this. Okay, so we had asymptote at pi. That's right in the middle. And to the left of pi was going to positive infinity. So we have this kind of behavior around the asymptote. Okay, what was after asymptote? Periodic, we established that. X and y intercepts, so 0, 0 is the y-intercept. And then x-intercepts at the even multiples. So we have an x-intercept here and an x-intercept here. So to actually notice, you know that it's going to be always positive, right? Why do you know that? Why is it always going to be positive in this part of the graph? Why can it never go negative? Similarly, it can't be positive here. Someone say why that's true. True, yeah, that is one reason, because the derivative is always positive. Yeah, that's probably enough. What else? If you didn't know the derivative was positive, just knowing that you have an going up towards infinity here and an x-intercept here, and no other x-intercepts. How would you know? Yeah, that's also true. Well, I'm looking for, well, sine you don't know, right? Sine can switch. I was looking for intermediate value theorem. If something's positive on an interval where there are no x-intercepts, then it's always positive on the interval. So that's regardless of derivative, but that is also true. The derivative is always also positive, so that's also a reason. Does that make sense? So that would be like your pre-calculus reason. I mean, which is also a calculus reason. Anyway, so okay, let's look at our derivative. Symmetry is odd, so we can get that in there. No critical numbers. All right, so yeah, let's look at the concave up. The concave up from 0 to pi, and then concave down. So that means it's going to go up like this. And it's concave down here. And that's it. And then you might want to graph a little bit more to really show the inflection. So there's another asymptote at negative pi. So that's why it's concave down here. See, it's concave down. And then, look, I'm doing the same picture over here, right? That's why, because of periodicity. This kind of looks like a function you know, right? So yeah, so that's the graph. We have an inflection point at the x-intercepts. We have vertical asymptotes at odd multiples of pi. What graph does this look like? Yeah, it kind of looks like tangent, but it's different, right? Because our asymptote's at pi, not at pi over 2 like they normally are. Okay, so why don't we take a 5-minute break, meet back at 6:45. But if you want to work on the next one, here it is. We're going to do this one next. All right, so then let's just start with this one, get a radical example. Okay, so let's just start with a domain. That usually explains a lot of things. What's the domain of this function? Or if not right away, just say, how do you find the domain of this function? What will be like your first step be? And remember, with domain, the question is like what's not in the domain. What's bad about radical functions? We have to be careful about. Yeah, so it's going to be the square root 2 and negative square root 2. And why is that? Because for radical functions, the radicand must be always greater than or equal to 0. So good for the square brackets. So just solving for that, you have 2 greater than x squared, and then square root of 2 greater than x squared, or greater than x. And then when you have the minus, it would be negative square root of 2. So just putting in nice order, negative square root of 2 and x and square root of 2. So that is negative square root of 2 and square root of 2. Good. Okay, so we don't have to graph a lot. That's nice. So only have to graph on this small little region. So it's a lot different than our periodic function. In this case, we only have to graph there. Okay, so what was the x and y intercepts? Okay, what's the y-intercept? Yeah, 0. X-intercept? How do you find x-intercepts? Yeah, set y equal to 0. So 0 is equal to x square root of 2 minus x squared. So what are the x-intercepts? When we have a product equal to 0, no matter what the product is, then we can do something. Correct. 0 square root 2 negative square root 2. So you set each factor to 0. It's always what you do for x-intercepts. So x equals 0, and square root of 2 minus x squared is equal to 0. So that's 0, and then this one is plus or minus square root 2. So we have 0, square root of x, square root of 2, and negative square root of 2. Okay, what's after this one? Is it symmetry? I forget. Oh, it's over here. Symmetry, yes. Let's do a new page. I already forgot what it was. 2 minus x squared. Okay, what do you do with symmetry? Plug in negative x. So what's our answer? What's the symmetry, if any? Correct, it's odd symmetry. So it's negative x, and then negative x squared is just x squared. Okay, so it's odd symmetric. So that's nice. So we have even less we need to graph. So graphing on 0 to radical 2 is enough, right? Because then you just reflect. Okay. What was after symmetry? There's no period. Let's do asymptotes. Are there any asymptotes? Well, yeah, you tell me. Are there asymptotes? Are there asymptotes of this function? Yeah, nope, none. Right, the only, there's no problems with this function, right? It's, if you're not in the, if you're, the only problem is like outside the domain, but right at the edge of the domain, it's an x-intercept. So nothing's going off to infinity. You don't have to care about, since our domain is negative square root 2 to root 2, you don't have to worry about horizontal asymptotes. And because you say the domain is negative root 2 to root 2, there's no vertical asymptotes, right? There's no problem in between. That's fine. So now we do calculus. So increasing, decreasing. Okay, how do you do increasing, decreasing? So we did this one, so I'll just say it. It's the derivative. Yeah. What rule do you need for the derivative here? Good. Yes, product and chain. So first and foremost, it's a product. So let's do derivative of x is just 1. So we have 2 minus x squared plus, and then x times the derivative of this. So yes, by the chain rule, it's 1/2 2 minus x squared to the negative 1/2, and then negative 2x. Okay, so this is, so we have a 2 and a 2 cancel. So we have negative x squared on top, and square root of 2 minus x squared on the bottom. Okay, can we simplify this? How could you make this nicer? Should I just leave my answer like that, or should you continue? Yes, combine the denominator. So it's nice that the denominator is the same as the numerator. So we get 2 minus x squared minus x squared over 2 minus x, root 2 minus x squared. So this gives 2 minus 2x squared over root 2 minus x squared. Okay. I can't do anything else, right? No, I don't think so. Okay, so that's my derivative. Now, can I factor this to make it easier for a first derivative test? Yeah, pull out the 2, and then what else? Now what? You can continue to factor. Oh, yeah, you could do that. You don't have to. I'm just looking at just factoring. Yeah, you just do 1 plus x, 1 minus x. Usually rationalizing numbers is nice, but you don't really have to rationalize unless it really calls for it. Functions. Um, unless you suspect it might simplify. No, no, it wouldn't simplify because if you're multiplying by a radical expression, you can't do anything here. And then you just get 2 minus x squared. Okay, so this is good enough. Okay, so what are the critical numbers? Yeah, 1 and -1. Are there any other critical numbers? Yeah, and also the does not exist places. Do these points exist in the function? So they don't exist in the derivative, but do they exist in the function? They do, right? So this is an example of a critical number that exists in the function, but not in the derivative. Okay, so we have our domain negative root 2, and then root 2, positive root 2. 1 and -1 are good. Always good thing to check, right? These are less than 1 or less than root 2, so they do exist inside. Okay, now let's use our factored form to do test values. Okay, always start with 0 because that's the easiest. All right. First of all, square root is always positive, right? As a function, square root is always positive, so we don't really care about that part of the function. The numerator is all we care about. Okay, so what's happening in this interval? Positive, yes. What's happening in this interval? So you're plugging in a value that's bigger than 1. Negative, yes, because this first term is negative. Then how about in this last interval? You're plugging something less than -1. Positive, yeah. Actually, no. The first term is positive, right? You plug something less than -1 that makes this first term is positive. But this term is negative. Yeah. Okay, cool. So do you have so it's increasing on -1 to 1, decreasing on negative root 2 to -1, union 1 to root 2. And what's the local max and min, if any? What is it? Yes, max is 1, yes. 1 f of 1. And min is -1. Okay, so we can just do these right now. So it's 1. When you plug in 1, you get 1 square root of 1. It's 1, 1. When you plug in -1, it's -1, 1. Questions on that? Using the first derivative test? Okay, let's look at the second derivative now. So, and we need the first derivative. What's the better form? Maybe this one here. All right. So 2 minus 2x squared over square root of 2 minus x squared is equal to f prime. Okay. So first of all, it's good to factor out that 2 because when we do derivatives, we can factor out constants. So now when we take the second derivative, it's going to be 2 times and then use the quotient rule. So derivative of the numerator is -2x, and times the denominator is 2 minus x squared, plus the numerator, then times the derivative of the denominator. All right, what is that? 1/2 2 minus x squared to the -1/2, and then -2x. And all over 2 minus x squared. Okay, so let's simplify this. So first term can't be simplified, -2x, 2 minus x squared, plus, okay, so what do we have here? We have a 2, 2 cancel. We have -x times 1 minus x squared, and then radical 2 minus x squared. Oh, yeah, that's... Okay, what can we do from here to simplify further? What can we do? How do you deal with complex fractions? What's usually the go-to? How do you simplify? Okay, let's see what you say first. Yeah, so how do you de-radicalize? So you can de-radicalize by just viewing this as a complex fraction. So you can do this all in one step. So you don't need to take the individual fraction and radicalize it. Or rationalize it, is the word. I'll give you a hint. So it's not very complicated, but in essence, it's really just like a plus 1 over b over c. How do you simplify that? Yeah, exactly. You would multiply top and bottom by the denominator part. So just like in this case, you would multiply top and bottom by b over b, or by b. Okay, by doing that, a lot of nice stuff happens. We get rid of the radical here, so -2x. Get rid of meaning it becomes not radical. this place we actually do get rid of the radical. So this is minus x, 1 minus x squared. And what's the denominator? What's the power of the denominator? Three halves, yes. You have a 1 from here, and then a 1/2 from here. Okay, so let's simplify this a bit. You can pull out a negative x, see that? So you pull out a negative x, you get 2 minus x squared, plus 1 minus x squared, over 2 minus x squared to the 3 halves. This is 4 minus 2x squared plus 1 minus x squared. Okay, further simplifying it, we get negative 3x squared plus 5. Okay, it's not as nice as hoped, but yeah, it's still good. All right, so questions on that second derivative? All right, so what are the, how do you do the second derivative test? What do you do now? Yeah, set it equal to 0. And undefined. All right, so well, undefined points are root 2, negative root 2. Okay, where is it equal to 0? Where is equal to 0? Sorry, I made a mistake. Oh, no, I didn't. I thought that was something else. So where is it equal to 0? Yes, so 0 from the first factor here. And then, yeah, negative square root of 5/3 and square root of 5/3. Okay, since we have a domain, we should probably check if these are in the domain. Are these in the domain? Do you remember a good way to check if they're in the domain? Is square root 5/3 bigger? Yes, good. It's within 6/3, so it's good. All right, so we have negative root 2, negative root 5/3, 0, root 5/3, and then root 2. Okay, so let's test some values. What's a number that's less than root 5/3? It's a nice number. Yeah, 1. Root 3/3 is 1, so 1 is fine here. Negative 1 is here. Okay, so when you plug in 1, what do you get? So you get a negative from the first factor. The denominator is always positive. Is it? Yeah, it has to be, because you're square rooting. And what's the numerator? It's positive. When you plug in negative 1, you get a positive and a positive. Okay, so now we think of a number between well, actually, you don't really need to think too much. We know that the first factor is always going to be negative when you plug in something positive. So all we have to check is that if you plug something that's bigger than radical 5/3, what is this term going to be? Like plug in, what's something that's big? What's radical 6/4? Is that bigger? Do you think? No, it's not. Or 7/8 or something. No, it's 7/8. Number I'm trying to think of. 9/8. Sorry, a brain moment. 7/4. That's fine, right? That's after 5/3 and below 2. Yeah. Okay, yeah. So we plug in something like that. So when you square it, this is going to be bigger, right? Negative 3 times 5 minus x squared. When you plug something that's bigger than radical 5/3, it's going to be negative. When you plug something less than radical 5/3, it's going to be positive, because this turns at this at radical 5/3. There's the x-intercept. All right, so this one will be positive and then negative. Okay, so this is concave up. That one and this one. And concave down. This one and this one. Oh, not negative 1. That was just their test value. And then inflection. Everything is an inflection point, right? Well, not radical 2 and negative radical 2. So there's really no change there. So just negative radical 5/3, 0, and radical 5/3. Okay, So any questions on that? Yeah, the second derivative got a little messy, but so it was a little hard to check the signs, but we got it. Any questions on second derivative? All right, so let's start to graph this. I'll type this, and then we will not have time for another one, so after this we can be finished. But I do have other ones you could look at on your own. All right, so let's give ourselves some room. Let's make this negative radical 2. This one radical 2. Y-intercept was 0, 0. And the endpoints. By the way, since you have a 0 and a 0 here, by Rolle's theorem, there should be a 0 derivative somewhere, which I think we do establish, right? Yep, 1, 1, and negative 1, 1. So let's make this negative 1, this 1. So we have negative 1, negative 1, and we have 1, 1. So these are maxes and mins. Okay, symmetry. So when we graph this, the right-hand side should look like the reflected of the left-hand side. Okay, it's increasing from negative 1 to 1. So it's going up this way, down this way, up this way, down this way. Yes. Okay, and then we have our inflection points. So we need a point here. Oh, wait, I don't think we actually graphed the point. What was it, 5/3? Radical 5/3. What was the function? 2 minus 5/3. So whatever that is, radical 5/3, and then that is 1/3. So this is radical 5/3. Okay, what's radical 5/3? That's definitely less than 1. So let's say that's like around here. Let's make these the inflection points. Okay, and then where's the concavity? It starts concave up, and then it's concave down from, oh, I'm sorry, it starts concave down up until negative root 5/3, so it's something like this. And then it switches to concave up to 0. So it hits this max, and then it goes up to 0. And I believe it changes concavity here. From 0 to 5/3, it's concave down. So that is, sorry, not, so like, up, and then concave down up here, and then it's going to be concave down until the radical 5/3. So here's concave down until radical 5/3, and then it's going to turn concave up to 2. All right, a bit tricky one. All right, as a correction to, I did the quotient rule formula wrong. This is a minus. So this should be a minus which makes this a plus. Which makes this a minus. Which makes this minus and a plus. Which makes this different. Makes it 3 minus x squared. So by doing that, our only inflection point is 0. Because the other roots of the second derivative are outside the domain. Radical 3 is outside. So by testing 1 and -1, like which are fine to test, we get a negative and we get a positive. Okay, so in our graph, we don't have these inflection points here. It just goes up. And that's it. All right, as a correction to, I did the quotient rule formula wrong. This is a minus. So this should be a minus, which makes this a plus. Which makes this a minus. Which makes this minus and a plus. Which makes this different. Makes it 3 minus x squared. So by doing that, our only inflection point is 0. Because the other roots of the second derivative are outside the domain. Radical 3 is outside. So by testing 1 and -1, like which are fine to test, we get a negative and we get a positive. Okay, so in our graph, we don't have these inflection points here. It just goes up. And that's it. All right, as a correction to, I did the quotient rule formula wrong. This is a minus. So this should be a minus, which makes this a plus. Which makes this a minus. Which makes this minus and a plus. Which makes this different. Makes it 3 minus x squared. So by doing that, our only inflection point is 0. Because the other roots of the second derivative are outside the domain. Radical 3 is outside. So by testing 1 and -1, like which are fine to test, we get a negative and we get a positive. Okay, so in our graph, we don't have these inflection points here. It just goes up. And that's it.